Hello, welcome to another module in this massive open online course. In this module, let us start looking at a new topic, and that is of convex functions. Alright, so we want to start looking at another important aspect or building block of the optimization framework that we want to eventually build, and therefore we want to start looking at convex functions, because these are going to be an important part of the optimization problems that we are going to consider. Okay. Now, what is a convex function? A convex function, for instance, can be defined as follows: consider a function f of x bar. Now, x bar, this can be simply f of x or it can be x bar. In general, it can be a vector. Okay. So, you can also have f of x, but in general you can have f of x bar, that is a function of a vector. Now, let also the domain of f, that is the set over which it is defined, domain of f is a convex. We have already seen what is a convex set. So, the domain of f is a convex set, okay, plus f is, now f is convex if the following property is satisfied. If you have 2 points x1 bar and x2 bar, and you take a convex combination theta times x1 bar and 1 minus theta times x2 bar, and you evaluate the function at that convex combination, that has to be less than or equal to the convex combination of the values of the function itself at x bar, x1 bar and x2 bar. So, that would be 1 minus theta f of x1 bar plus 1 minus theta f of x2 bar. So, what we must have is that for f to be convex, it must be the case that f of, for 2 points x1 bar x2 bar that belong to the domain of f of theta times x1 bar plus 1 minus theta times x2 bar must be less than or equal to theta times f of x1 bar plus 1 minus theta times f of x2 bar. This can be represented pictorially as follows. To better understand this, look at the following picture. Okay, it can be seen pictorially as below. I am just going to draw a diagram that will better illustrate this. So, let us say we have a function that looks like this. Let us take 2 points, okay, and let us join. Now, this is your f of x. Let's consider a simple one dimensional x. Let these two be the points. Let this be your point x1, correct. So, this is your point x1 and this is your point x2, and let us take a convex combination of x1 and x2 that lies along the line. So, this is your theta times x1 plus 1 minus theta times x2, okay. And this value, if you look at this value, this is your f of theta times x1, that is the value of the function at theta times x1. This is the value of the function this is your f of theta times x1 plus 1 minus theta times x2. Now, on the other hand, look at this point is f of x1, that is one end of this chord, and this point is f of x2, and we know now that if you take a convex combination, that represents the line segment, correct. So, therefore, we now consider the line segment that is joining these points f of x1 and f of x2, and theta times f of x1 plus 1 minus theta times f of x2 is this point, theta times f of x1 plus 1 minus theta times f of x2 is this point, and you can see therefore that theta times f of theta times x1 plus 1 minus theta times x2 is less than or equal to theta times f of x1 plus 1 minus theta times f of x2, which in essence is basically saying that, if you think about this, what this is essentially saying, that if you take 2 points on the function, join them by a chord, the chord always lies above the function. So, if you take 2 points x1 x2, join the chord, right, between f of x1 and f of x2, the chord joining f of x1 and f of x2 always lies above the function between these 2 points x1 and x2. That is a very that is an intuitive definition of convexity. So, the convex function curves upwards, it looks like a ball, all right, your regular ball, typically a convex function looks like a ball that curves upwards, although that is not always the case, but typically when you think of convex functions, the prototype of a convex function is a ball kind of a function which curves upwards. Okay. So, this basically shows that your f of theta times x1 plus 1 minus theta times x2 is less than or equal to theta times f of x1 plus 1 minus theta times f of x2. Okay. So, this is your definition of convexity, and this is what you can see from. So, this is your convex function. Typically, convex function looks like a ball that curves upward. It looks like a ball. Okay. And what this means intuitively, the intuition is that the chord joining f of x1 comma f of x2 lies above the function, the curve or the plot of the function between x1 and x2, all right. So, the chord that is joining x1 and x2 lies, the chord joining f of x1 and f of x2 lies above the function between x1 and x2. Okay. And this is a very important class of functions that we will frequently encounter. In fact, most of our optimization problems will be built on convex functions, all right. Therefore, it is very important to understand the definition of a convex function and also the various properties of convex functions. Okay. All right. On the other hand, now naturally a concave function is one which is Now, for a concave function, again it is important to remember that if you look at a function of f x bar, the domain has to still be convex, okay, either concave or convex. The domain, that is the set over which it is defined, is convex, and if minus f is convex, then f of x bar is concave. Alright, so f of x bar is concave if the domain is convex and minus of f is convex. Naturally, this implies that f of theta times x bar plus 1 minus theta times x bar is greater than equal to theta times f of x bar plus 1 minus, I am sorry, x1 bar x2 bar theta times x1 bar plus 1 minus theta times x2 bar, f of that is greater than equal to theta times f of x1 bar plus 1 minus theta times f of x2 bar. Okay. And naturally a concave function curves downward, so its curvature is down. So, it looks like this, and you can clearly see that the chord, if you look at the chord joining any 2 points, the chord lies, the function lies above the chord. Okay. So, this is function lies above the chord for a concave function. This is your concave. Okay. And we can now look at several examples to understand this notion of concave and convex functions better. The simplest example is that, the most simplest example is that of a straight line. If you look at a straight line, you take any 2 points on the straight line, the chord itself lies on the function, so the chord neither lies above nor below, so the chord coincides with the function. So, you can say the straight line is convex as well as concave. So, the straight line is in fact convex, and it is also concave for that same matter, because the function coincides with the curve, coincides with the chord joining any 2 points. So, this is convex, and this is also concave. So, any straight line is convex and also concave. Okay. A convex function, or what you can also say is a strictly convex function, that is curves upwards, and a very important class of such functions is the exponential function. If you look at this, this is e to the power of ax for a greater than 0. Okay. It is also known as the exponential . This is the exponential function, and you can clearly see, once again, you take any 2 points, the chord lies above the function, and therefore, this is, of course, we are going to do see later a rigorous test to establish convexity or concavity, but right now based on our intuition, you can clearly see this is a convex function and this exponential function, there is an increasing exponential which is a convex function. It is an important class of convex functions, and in fact one can also consider a decreasing exponential, that is e raised to the power of ax, that arises for a less than 0, and we will also, you will also see you can also quickly see just by visual inspection that that is also a convex function. Okay. So, what happens if it is not very difficult to see, if you plot e raised to the power of, this is your e raised to the power of a x, a less than 0, also an exponential, and you can again see that take 2 points, join the 2 points, the chord, okay. You take any 2 points and you join the 2 points, the chord lies above the function, and therefore, this is a convex function. And of course, if a equals 0, this becomes e raised to 8 e raised to the power of 0, which is 1, which is again a convex function. So, one can say e raised to the ax in general for any real value of a is a convex function. Okay. So, one can conclude that e raised to x for any value of a, the exponential function for any value of a is a convex function. If a is less than 0, it is decreasing. If a is greater than 0, it is increasing. Okay. But in any case, it is a convex function. Let us look at the power. X to the power of alpha, if alpha is greater than or equal to 1, this was defined for x greater than or equal to 0, alpha greater than or equal to 1, or alpha less than or equal to 0. In both cases, you can see it is convex. For instance, if you look at f of x equals x square, you can see, you are well familiar that this is a classic bowl shaped function. In fact, f of x equal to x square, you can define it for entire minus infinity less than x less than infinity, and it looks something like this, correct. And at x equal to 0, it is 0, and this is your classic example of a convex function. This is f of x equals x square, and you can clearly see if you join any 2 points by a chord, it lies above the function. So, this is a classic example of a convex function. In fact, it looks like a perfect bowl. This is your f of x equal to x square. Okay. And now, on the other hand, if you look at f of x equal to x cube, now you might be under the misconception that f of x equal to x to the power of alpha for alpha greater than equal to 1 is always convex. But if you look at f of x equal to x cube for x less than 0, this is negative. For x less than 0, this is negative, and x greater than 0, it is positive. But you can see here x greater than 0, the chord lies above the function, but for x less than 0, the chord lies below the function. So, the x less than 0, it is concave. And for x greater than 0, it is convex. So, this is only convex for x greater than equal to 0, f of x cube. So, that is why it is important to consider the suitable domain. So, this is now convex. F of x equal to x cube for x greater than equal to 0 is convex, and in this region x less than equal to 0, it is concave. Further, one can show that well, we can check this later, that is any norm x bar to the base p p greater than or equal to 1, this is of course a function of a vector, this is convex. We will keep this for later, but this is important, that is the norm, p norm for p greater than or equal to 1, this is convex. Okay. So, we have seen several examples of convex functions, very straightforward, mostly one dimensional function, mostly functions of a single variable. So, we have seen that the exponential function is convex, the straight line of course is convex and concave, exponential function for all values of a is convex, x square is convex over the entire real line, x cube is convex only if x is greater than or equal to 0. Let us look at examples of concave functions. Now, the classic example of a concave function the classic example is ln x, or basically log of x, the natural logarithm is also known as the natural logarithm log x to the base e. And if you draw this, it is only defined for of course x greater than or equal to 0. If you draw this at x equal to 1, it becomes 0. And at x equal to 0 it tends to minus infinity, and as x tends to infinity it tends to infinity. And if you look at any 2 points join the chord, the function always lies above the chord, this is concave. In fact, the right way to do it is you have to look at f of minus of f of x. So, if you look at minus of f of x, so this is your f of x, minus of f of x, because as per our definition, remember minus of f of x, if minus of f of x is convex, then f of x is concave, and if you plot minus of f of x, then that looks like this. This is 0 at x equal to 1, as x tends to 0 tends to infinity, as x tends to infinity tends to minus infinity. So, this is minus of the natural logarithm of x, the chord lies above the function. So, this is convex, correct. So, minus natural logarithm is convex, and this implies that the natural logarithm of x equals is a concave function. Okay, that is the technically the correct way to demonstrate concavity. Another important class of concave functions is f of x equals x power alpha for 0 less than alpha less than 1. Okay. And in fact, for example, let us take alpha equal to half, we have f of x equals square root of x, and naturally this is defined only for x greater than or equal to 0, correct. So, we will restrict the domain here to x greater than or equal to 0, and if you plot square root of x for x greater than or equal to 0, it looks something like this, and you can once again see the function lies above the chord. So, this is square root of x, correct, square root of x, and this is convex. Okay, this is your function f of x equals square root of x for x greater than equal to 0, it is convex. all right. So, in this module we have seen a very important definition, that of convex and concave functions. I urge you to go through this once again and understand it thoroughly, because we are going to invoke this and use this property very frequently. Thank you very much.